Picture this. It's 1936, and a Belgian engineer walks into Chrysler's Detroit headquarters with blueprints for an engine that automatically adjusts its compression ratio while running from 6:1 all the way to 16:1, hundreds of times per minute based on load and fuel quality. Chrysler's engineers tested it, confirmed it worked exactly as claimed, and then spent the next 5 years burying it. This is the story of Henri Thuveno, the Belgian genius who solved internal combustion's biggest problem in 1935, and how Detroit proved that sometimes the worst enemy of progress is success itself. The problem with fixed compression. Before we get to Thuveno's brilliance, you need to understand why compression ratio is the holy grail of engine design. It's literally the single most important number in determining an engine's efficiency and power output. Higher compression means more power, better fuel economy, cleaner combustion. It's thermodynamics in its purest form. Here's the problem. In a conventional engine, the compression ratio is fixed. It's determined by the physical relationship between the piston's top dead center and bottom dead center positions. Once the engine is built, that number is locked in forever. And that creates a massive engineering compromise. See, you want high compression for efficiency. Diesel engines run 16:1 or higher, which is why they're so fuel efficient. But gasoline engines in the 1930s could barely handle 6:1 before they'd detonate themselves into expensive paperweights. The octane rating of fuel back then was pathetic. 65 octane was premium. Knock, ping, pre-ignition, these weren't occasional problems. They were constant threats. So, engineers had to compromise. They'd design engines with compression ratios low enough to run on the worst fuel anyone might put in them. This meant leaving huge amounts of efficiency on the table. If you had access to better fuel, your engine couldn't take advantage of it. If you were cruising at light load, where high compression would be perfectly safe, you were stuck with the same ratio needed for full throttle acceleration. It was like being forced to wear the same clothes whether you're going to the beach or climbing a mountain. The outfit has to work for everything, which means it's optimal for nothing. Detroit knew this was a problem. Everyone knew. But the solution seemed impossible. How do you change the fundamental geometry of an engine while it's running? The piston has to stop at exactly the same point every revolution, right? The connecting rod has to be a fixed length. The crankshaft throw is what it is. These are mechanical certainties like gravity or death. By 1935, the industry had accepted fixed compression ratios, the way they'd accepted that engines needed crankshafts and wheels needed to be round. It was just how things were. Optimization meant finding the best compromise, not eliminating the compromise entirely. Then, Henri Thuveno said, "Hold my beer." Enter Henri Thuveno. Henri Thuveno was nobody's idea of a typical automotive engineer. Born in Belgium in 1898, educated in Brussels during World War I, he was a mechanical engineer who'd spent the 1920s working on industrial machinery, pumps, compressors, hydraulic systems. Nothing sexy, nothing automotive. But Thuveno had a gift for seeing fundamental problems that everyone else had learned to ignore. While Detroit engineers were incrementally improving conventional engines, making them smoother, more reliable, slightly more powerful, Thuveno was asking the kind of first principles questions that make established experts uncomfortable. Why does the piston have to stop at the same point every cycle? It doesn't, really. The piston stops wherever the connecting rod and crankshaft geometry dictate. But what if you could change that geometry dynamically? In 1933, Thuveno filed his first patent for what he called an articulated piston. The patent drawings looked like something from a fever dream. A piston that wasn't really one piece. A connecting rod that wasn't really rigid. A mechanism that seemed to violate basic mechanical principles. Every engineer who saw it had the same reaction. That can't possibly work. There's no way to control it. The forces would tear it apart. The complexity would make it unreliable. And even if you could build it, why would you? Thuveno's response was simple. He built one. In a small machine shop in Brussels, using 1930s tooling that would make modern machinists weep, he constructed a working prototype. And it didn't just work, it worked beautifully. By 1935, he had a single-cylinder engine that could adjust its compression ratio from 6:1 to 14:1 while running. It didn't vibrate itself apart. It didn't leak. It didn't explode. It just worked, smoothly and reliably, doing something that every expert said was impossible. Word spread. European automotive journals published articles. Engineers made pilgrimages to Brussels to see this mechanical unicorn. And eventually, inevitably, someone from Chrysler Corporation got on a boat. The impossible design. Thuveno's articulated piston design was brilliant in the way that truly revolutionary ideas are brilliant. Once you understand it, you wonder why nobody thought of it before. But before you understand it, it seems like black magic. The core concept was this. Instead of a single rigid piston connected to a fixed-length rod, Thuveno split the piston into two pieces. The upper section was a conventional piston crown that sealed against the cylinder walls. But underneath that crown was a secondary piston, a smaller diameter piece that could telescope inside the upper section. Think of it like a piston within a piston. The upper crown handled combustion pressure and sealing. The lower section connected to the connecting rod, and between them was a hydraulic chamber that could push them apart or let them collapse together. When the hydraulic chamber was pressurized, it forced the two sections apart, effectively making the piston taller. This raised the top dead center position, increasing compression ratio. When pressure was released, the combustion forces pushed the sections back together, lowering compression. But here's where Thuveno's genius really showed. He didn't just make it adjustable, he made it automatic. The hydraulic pressure was controlled by a mechanical governor linked to throttle position and engine speed. More throttle, more fuel, higher risk of knock. So compression automatically decreased. Light throttle, cruise conditions, low knock risk, so compression automatically increased. The system could adjust hundreds of times per minute. It wasn't crude or stepped. It was infinitely variable across its entire range. The engine essentially optimized itself continuously, always running at the highest compression ratio that was safe for current conditions. The technical execution was insane for 1935. The hydraulic system used engine oil pressure, regulated by a precision valve body that would have been more at home in an aircraft. The piston crown had special ring grooves that maintained seal integrity even as the piston height changed. The rod bearing had to accommodate the constantly varying geometry without binding or wearing excessively. Thuveno used bronze bushings for the telescoping sections, graphite impregnated to reduce friction. The hydraulic chamber had leather seals because rubber compounds in 1935 couldn't handle the heat and oil exposure. The control valve was a masterpiece of precision machining, with clearances held to 0.02 of an inch using manual tooling. The first prototype weighed about 40 pounds more than a conventional piston and rod assembly, but that extra weight bought you something impossible. An engine that could run on 60-octane fuel at 6-to-1 compression, then automatically optimized to 12-to-1 when conditions allowed. The implications were staggering. You could build one engine that performed like multiple engines. High compression efficiency for cruising. Low compression reliability for full throttle. Optimal performance regardless of fuel quality, altitude, or load. It was adaptive engineering decades before computers made adaptation easy. How it actually worked. Let me walk you through exactly how Thuveno's system functioned, because the details are where the genius lives. We're going to get technical here, but stick with me. This is important. The piston was split into two pieces. The upper section was a conventional piston crown with standard rings, but underneath was a smaller diameter piston that telescoped inside the upper section. Between them was a hydraulic chamber. Oil pressure pushed them apart, increasing compression, drained the pressure, and combustion forces pushed them together, lowering compression. The connecting rod attached to the lower section. This was critical. The rod never moved relative to the crankshaft. The varying piston height happened above the rod connection point. No variable length rods, no crazy linkages, just a piston that could change its effective length. The hydraulic control was the real masterpiece. Thuveno used a mechanical governor driven by the distributor shaft that sensed engine speed and throttle position. At light throttle, full oil pressure flowed into the hydraulic chamber, maximum piston extension, 14-to-1 compression, thermal efficiency in the mid-30s, which was absolutely insane for 1935. But the moment you opened the throttle for acceleration, the governor bled pressure from the chamber. The piston sections collapsed together. Compression dropped to 6-to-1 at full throttle. This happened in fractions of a second. The piston could change height by nearly half an inch in a single revolution. Drivers reported no vibration, no surge, nothing beyond normal acceleration. The system was self-compensating for fuel quality. Low-octane fuel would cause knock, which the governor interpreted as a signal to reduce compression. The engine automatically found the highest safe ratio. Premium fuel, compression crept higher until it found the new limit. No tuning required. The engine just figured it out. Thuveno needed 500 psi in the hydraulic chamber. Standard oil pressure was 30 to 40 psi. So, he added a small gear pump driven by the distributor shaft. The whole assembly added 12 pounds to the piston weight. For a 600-pound engine, this was negligible. The numbers that terrified Detroit. When Chrysler's engineers finally tested Thuveno's engine in 1937, the results were so good they thought the instruments were broken. They recalibrated everything and tested again. Same results. They built a second prototype. Same results. The numbers were undeniable, and they were terrifying. Thermal efficiency. A stock Chrysler Flathead 6 from 1937 achieved about 23% thermal efficiency. That means 77% of the fuel's energy went out the tailpipe as waste heat. This was considered normal, good even for the era. Thuveno's variable compression engine hit 38% thermal efficiency under optimal conditions. That's a 65% improvement. For the same amount of fuel, you got 65% more useful work. In practical terms, a car that normally got 15 miles per gallon would get 25. Power output. The test engine was a modest 3.5-liter inline-six. In fixed compression form, with a 9-to-1 ratio, it made 90 horsepower. That was the highest compression you could safely run on premium pump gas in 1937. With variable compression, the same engine made 90 horsepower at 6-to-1 for reliability, but 120 horsepower at 14-to-1 during cruise. You got the reliability of a low compression engine with the efficiency of a high compression engine. It was having your cake and eating it too. Emissions were dramatically cleaner. Higher compression meant more complete combustion, less unburned hydrocarbons, less carbon monoxide. The exhaust from the variable compression engine was noticeably less noxious than a conventional engine. One test report noted that you could stand behind the running engine without your eyes watering, which was not true of normal cars. Fuel flexibility was the real killer app. The test engine ran successfully on fuel ranging from 60 octane to 85 octane without any adjustment or tuning. Just pour it in and drive. The engine automatically compensated. For a market where fuel quality varied wildly by region and season, this was revolutionary. Operating temperature was lower. Higher thermal efficiency meant less waste heat. The cooling system could be smaller and lighter. Water temperature ran 15 degrees cooler than a conventional engine under the same load. This meant improved reliability and longer oil life. The cost projections were where things got complicated. Chrysler's accountants estimated that the articulated piston system would add about $75 to the manufacturing cost of an engine. In 1937, that was real money. A complete Chrysler 6-cylinder engine cost about $200 to build, but the fuel savings were equally real. At 1937 gas prices, the system would pay for itself in fuel savings in about 18 months of typical driving. After that, it was pure profit for the owner. Over the life of the car, the savings could exceed $500. Corporate finance ran the numbers. If Chrysler offered variable compression as a standard feature, they could charge a $100 premium, and customers would still save money. If they offered it as an option, penetration rates would be lower, but profit margins higher. Either way, it was a winner, or it should have been. Chrysler's involvement. Chrysler's relationship with Thuveno started optimistically in late 1936. Carl Breyer, Chrysler's chief engineer and one of the most innovative minds in Detroit, saw the European patents and immediately recognized their significance. He convinced Walter Chrysler himself to fund a licensing agreement. The deal was straightforward. Chrysler would pay Thuveno a modest licensing fee and royalties on any engines produced with his system. In exchange, they'd get exclusive North American rights. Thuveno kept European rights, where he was negotiating with several manufacturers simultaneously. Chrysler built their first prototype in early 1937. They assigned a team of 8 engineers, led by a brilliant but skeptical engineer named James Zeter. Zeter's job was to find problems, to prove why the system wouldn't work in production. He failed spectacularly. Every test validated Thuveno's claims. The engine ran reliably. The efficiency gains were real. The system didn't fail even under abuse testing, where they deliberately tried to break it. Internal memos from this period, obtained years later through various archives, show genuine excitement. Engineers were writing things like revolutionary, game-changing, the future of automotive engines. This wasn't marketing hype. These were hard-nosed engineers who'd spent careers being skeptical of new ideas. But then something shifted. By mid-1937, the tone of the memos changed. Suddenly there were concerns about manufacturing complexity, about service requirements, about whether dealers could maintain such advanced technology. These were valid concerns, but they seemed to appear overnight, all at once. What happened was corporate politics. Chrysler had just invested millions in new engine manufacturing facilities designed for conventional engines. They'd committed to a new engine family that would carry them through the 1940s. Tools had been ordered, suppliers contracted, workers trained. The variable compression engine didn't just compete with that investment, it made it obsolete. If Chrysler adopted Thuveno's system, they'd have to scrap much of their new tooling and start over. The financial hit would be enormous, possibly tens of millions of dollars. Meanwhile, GM and Ford were having their own problems. The recession of 1937 had hammered auto sales. Nobody wanted to make big risky bets on new technology. The conservative play was to stick with proven engines and wait for the market to recover. Chrysler's board made a decision. They'd continue testing and development, but delay production indefinitely. They'd keep the patents locked up so competitors couldn't use them. And they'd quietly shelve the project until market conditions improved. Thuveno was still being paid his licensing fees, so he couldn't complain too loudly. But he knew what was happening. His innovation was being buried, not because it didn't work, but because it worked too well. The testing phase and results. Despite the corporate cold feet, Chrysler's engineers continued testing through 1938 and into 1939. They couldn't help themselves. The technology was too fascinating, the results too promising. Multiple test vehicles were built, and they logged tens of thousands of miles. One test mule was a 1938 Chrysler Imperial sedan with a variable compression straight 8. This car became legendary within the engineering department. It would routinely achieve 28 miles per gallon on highway runs, when normal Imperials struggled to hit 15. Yet, it could still out-accelerate the standard car when needed. Test drivers reported that the car felt normal to drive. No strange behaviors, no weird noises, nothing to indicate that something revolutionary was happening under the hood. The throttle response was actually better than standard engines because the system would drop compression at the first hint of knock, allowing more aggressive ignition timing. One memorable test involved a cross-country drive from Detroit to Los Angeles. The variable compression Imperial made the trip on 63 gallons of fuel. An identical standard Imperial, driven by the same driver on the same route immediately afterward, required 112 gallons. The fuel savings were so dramatic that Chrysler's accountants initially thought there was an error in the logs. The reliability testing was equally impressive. One test engine ran continuously on a dynamometer for 500 hours at varying loads and speeds. No failures. The hydraulic system needed one seal replacement at 300 hours, but that was it. The piston assembly showed minimal wear when disassembled for inspection. Durability testing included deliberate abuse. They'd run the engine at full throttle from cold starts. They'd cycle rapidly between idle and redline. They'd use the worst fuel they could find. The system handled everything. The governors would occasionally need adjustment after extreme abuse, but the core mechanism remained sound. Cold weather testing in northern Michigan showed that the system worked down to -20 Fahrenheit. The engine oil needed to be thin enough to flow through the hydraulic passages, but that was true of conventional engines too. Once warmed up, operation was completely normal. High-altitude testing at Pikes Peak revealed one of the system's best features. As atmospheric pressure dropped and knock resistance improved, the engine automatically increased compression to maintain power. A conventional engine would lose 20% power at Pikes Peak summit. The variable compression engine lost less than 10%. The service department did maintainability studies. They had regular mechanics, not engineers, perform oil changes and basic maintenance on the test vehicles. None of them even noticed the variable compression system. It was completely transparent to normal service procedures. By late 1939, Chrysler had overwhelming evidence that the system was production ready. It worked, it was reliable, it could be serviced, and the fuel economy benefits would sell cars. Everything pointed toward production. Then World War II started in Europe, and everything changed. Why it died. The death of Thuveno's variable compression engine wasn't a single event. It was a slow suffocation by circumstances, corporate conservatism, and spectacularly bad timing. First, the war. By 1940, Chrysler was pivoting to military production: tanks, aircraft engines, ammunition. Innovative civilian engines were nowhere near the priority list. The military wanted proven, reliable power plants, not experimental systems. The variable compression program went into hibernation. Thuveno himself faced bigger problems. Belgium was occupied by Nazi Germany in May 1940. As a prominent engineer, he was forced to work on German military projects. His variable compression patents, which were filed internationally, became inaccessible. The entire European testing program halted. After the war, the automotive world had changed. Fuel, octane ratings, had improved dramatically due to aviation fuel technology developed during the conflict. By 1946, premium pump gas was rating 80 to 85 octane. This meant engines could safely run 9-to-1 or even 10-to-1 compression without the variable system. The value proposition shifted. When fuel was 65 octane, the ability to vary compression from 6-to-1 to 14-to-1 was revolutionary. But with 85 octane fuel, you could just design a fixed 10-to-1 engine and be done with it. The benefits of variable compression were still there, but they were less dramatic. Manufacturing costs were another problem. Post-war automotive production was all about volume and efficiency. The industry was building millions of cars for a pent-up demand after years of wartime shortages. Adding complexity for a modest efficiency improvement didn't make sense when you could barely keep up with orders for conventional cars. Chrysler's corporate priorities had shifted too. They'd invested heavily in the Hemi engine, which debuted in 1951. The Hemi was a marketing sensation, a technological showcase that defined Chrysler's performance image. Variable compression, by contrast, was about efficiency, not power. It didn't fit the narrative of 1950s American automotive excess. There was also the cruel reality of American fuel prices. Gas was cheap in the 1950s, averaging around 25 cents per gallon. Fuel economy wasn't a selling point. Customers wanted power, style, and size. An engine that saved fuel at the cost of added complexity was solving a problem nobody cared about. Thuveno himself had moved on. After the war, he'd returned to industrial engineering, working on hydraulic systems for mining equipment. The automotive industry had burned him. His revolutionary invention had been tested, validated, and then abandoned. He'd seen the future and watched Detroit choose the past. The patents started expiring in the 1950s. Chrysler let them lapse without renewal. The technology entered the public domain, where it was promptly ignored by every manufacturer. A few engineering papers were published in academic journals, curiosities about an interesting dead end. By the 1960s, variable compression was a footnote in automotive history, an interesting idea that didn't pan out. Another might have been in an industry full of them. Except it wasn't a dead end, it was just early. The modern resurrection. Fast forward to 2017. Infiniti, Nissan's luxury brand, unveils the VC turbo engine. Variable compression, they call it. 2.0-liter turbocharged 4-cylinder, that can adjust its compression ratio from 8:1 to 14:1 while running. Sound familiar? The VC Turbo uses a completely different mechanism than Thuveno's articulated pistons. Instead of telescoping piston sections, it varies the compression ratio by changing the crankshaft geometry. A multi-link connecting rod setup powered by an electric actuator physically raises and lowers the piston's top dead center position. But the principle is identical. Variable compression for optimal efficiency at all operating conditions. High compression for fuel economy, low compression for turbocharged power. The exact same problem Thuveno solved in 1935, just with modern electronics and materials. Infiniti marketed the VC Turbo as revolutionary, the world's first production variable compression engine. Technically true, since Thuveno's engine never reached production, but philosophically, it's a hollow claim. The revolution happened 80 years earlier in a Brussels machine shop. The VC Turbo achieves about 35% thermal efficiency, slightly better than Thuveno's engine. But remember, Thuveno was working with 1930s materials, machining tolerances, and fuel. Scale his design to modern standards, and he'd probably hit 40% or better. Other manufacturers are following suit. Mercedes has patents for variable compression systems. Mazda's Skyactiv X engine uses variable compression achieved through combustion control rather than mechanical means. Even Formula One has explored the concept for their hybrid power units. The automotive world has finally caught up to Henri Thuveno. It only took 8 decades. The modern systems are more complex than Thuveno's design. They rely on electronic control, precise sensors, computer optimization. His system was purely mechanical, using hydraulic pressure and mechanical governors. In some ways, his approach was more elegant. Fewer things to break, no computers to crash, no sensors to fail. Would Thuveno's design work with modern materials and machining? Absolutely. Replace his leather seals with modern synthetics. Use computer-controlled hydraulic valves instead of mechanical governors. CNC machine the pistons to tolerances he could only dream of. You'd have a system that's simpler, lighter, and potentially more reliable than current variable compression engines. But here's the thing that really stings. If Chrysler had been brave enough to produce Thuveno's engine in 1938, the entire trajectory of automotive development might have changed. We'd have had high-efficiency engines decades earlier. The oil crises of the 1970s wouldn't have hit as hard. The push toward electric vehicles might have been delayed, as internal combustion became significantly more efficient. One engineer's innovation, properly deployed, could have reshaped an industry. Instead, it sat in patent archives while Detroit built bigger, thirstier, less efficient engines for 50 years. The legacy and lessons. Henri Thuveno died in 1973, shortly before the first oil crisis that would have validated everything he'd worked for. He never saw variable compression reach production, never saw his ideas vindicated. He spent his final years working on hydraulic mining equipment, his automotive innovation a distant memory. But his story matters for reasons beyond the technology itself. Thuveno's variable compression engine is a perfect case study in how industries resist innovation, even beneficial innovation, when it threatens existing investments and orthodoxies. Chrysler's engineers knew the system worked. They had the data, they had the test results, they had prototypes with tens of thousands of miles proving reliability. And they still couldn't get corporate approval for production because changing direction would cost money and require admitting that their current path was suboptimal. This is the innovator's dilemma in its purest form. Established companies struggle to adopt disruptive technologies not because they don't understand them, but because adopting them requires destroying their own infrastructure and expertise. It's easier to keep doing what you're doing, even when you know something better exists. The timing issue is equally instructive. Thuveno's invention came at the worst possible moment. Too late to catch the expansion of the 1930s. Too early for the war years. Too complex for the volume-obsessed 1950s. Too efficiency-focused for the excess of the 60s. It was right technology, wrong time, repeatedly. But imagine if one company had been brave enough. If Chrysler had launched variable compression in 1946, marketed it as space-age technology for the post-war world. They could have owned the efficiency market. They could have been the fuel economy leaders for decades. Instead, that distinction went to foreign manufacturers. Japanese companies built their post-war automotive industries on efficiency and quality. They didn't have variable compression, but they had the mindset that efficiency mattered. They listened to engineers like Thuveno instead of burying them. The broader lesson is about outsider innovation. Thuveno wasn't a career automotive engineer. He came from industrial machinery where hydraulic control systems were common. He looked at engine design without the biases and assumptions that trap Detroit engineers. This is why disruption so often comes from outsiders. They don't know what's impossible. They don't have careers invested in current methods. They can ask stupid questions that turn out to be brilliant. Why does compression have to be fixed? Because that's how we've always done it. That's not an answer, that's an excuse. Today, as we face another automotive revolution with electric vehicles, the lesson is more relevant than ever. Internal combustion isn't dead yet. Variable compression, combined with direct injection, turbocharging, and hybrid systems, could extend the viability of gas engines for decades. But only if companies are willing to invest in these technologies rather than just abandoning them for electric. The irony is that electric vehicles face similar resistance from established players today that variable compression faced in 1937. The technology works, the benefits are clear, but it requires scrapping existing infrastructure and expertise. History doesn't repeat, but it certainly rhymes. Henri Thuveno's variable compression engine reminds us that being right isn't enough. You need to be right at the right time, with the right backing, in the right market. Genius without timing is just an expensive hobby. Innovation without corporate support is just engineering masturbation. But it also reminds us that ideas don't die. Thuveno's patents expired, and his prototypes were scrapped. But the fundamental insight, that compression ratio should be variable to optimize efficiency, that truth survived. It waited in technical journals and patent archives until the world was ready. Sometimes the best ideas are just early. Sometimes revolutionary technology needs to wait for a revolution. And sometimes, just sometimes, a Belgian engineer in a Brussels machine shop can outsmart the entire American automotive industry, even if it takes 80 years to prove him right. So, here's to Henri Thuveno, the engineer who solved a problem nobody wanted solved, the innovator who was right too soon, the genius who proved that sometimes the biggest obstacle to progress isn't ignorance, it's success, comfort, and the unwillingness to change. Every time you read about a new variable compression engine, remember it's not new. It's just finally catching up to what one Belgian engineer figured out in 1935, while Detroit was busy building flatheads and telling themselves efficiency didn't matter. The future isn't always where you think. Sometimes it's in a Brussels workshop, gathering dust, waiting for the world to wise up.